Hi, welcome to lecture 6. So today we're going to talk about different programming languages and how they're the same and how they're different. So maybe it can get you a little bit thinking about just in ways that programming languages are similar and how they're different. So we're going to start out and we're going to skip section 6 and 7 at the end. Don't worry about those. We're just doing 1 through 5. So just as an FYI. Let's go ahead and jump headfirst into the historical perspective and where programming languages came from and where they're heading and things like that. So we talked a little bit about some programming languages back in lecture 2. We talked about machine language and we talked a little bit about assembly language. We did some of those exercises with that vol example with the opcode and the operand. And how difficult that was with translating it and telling the computer what to do. So assembly language is still difficult to understand. It's not as intuitive as more modern languages. One big disadvantage with the machine languages and the assembly language up till now is that they are both machine dependent. This means that programs had to be written multiple times and changed based on the hardware and the software of your computer or machine that you were using. This led to the invention and with computer scientists coming up with the third generation languages. And that's kind of where we're going to concentrate today, is on that third generation languages. They are machine independent. They can run on any computer, regardless of hardware, software. And some of those early languages you may have heard of are Fortran and COBOL. You'll hear those again in a few slides. After that step was taken, programming has become more powerful and more intelligent, quote unquote intelligent, as time goes on. So let's take a look at each of the generations again, and some of this will be a review of chapter 2. Let's start with our second generation language, and that's the assembly language. We talked a little bit at length in a couple lectures ago. It uses words or mnemonics, and I use words, the term words very, very loosely here, and that replaces the binary of the machine language. So but it is just a word-for-word representation of what the machine language needs, and of that binary, it is just a straight translation. Now, the opcodes are no longer in hex. Now they have short names, like you can see here in this example, of like move and length and start and things like that. Assembly was the first to use, variables or identifiers. And this is going to be those descriptive names of those specific memory locations. Now, we've taken variables to have a few different meanings. In mathematics, it holds a value. Well, in the computer world, it does hold a value, but really the definition is that you're referring to a memory space that contains the value. I believe we talked about that in a previous lecture too. These variables are making it much easier for a programmer to refer to these memory locations and to do, have descriptive wording, and just to better understand, what's going on. Now, some characteristics of assembly language include, of course, that one-on-one mapping between your non-binary and your binary. It is machine dependent because there is a conversion that needs to take place to change that code from the mnemonic into the binary. Because of this, the programmer has to think the way a machine thinks. And it's still not really easy to look at and understand. I think some are a little bit easier than others. But let's talk about that process of how, with assembly language, you change those mnemonics in letters into that binary. So assembly uses something called an assembler to translate those mnemonics into machine language for the computer to understand. Now, each language is going to have some sort of translation, because unless you're using machine language, but everything does have to do some sort of translation into machine language. So here's just an example of how assembly language looks compared to machine language. Yes, the machine language is difficult to understand, but that assembly language mnemonic, to me, not much easier. This is where that third generation of languages comes in and where it was developed. So your third generation languages uses syntax much closer to that pseudocode that we learned last lecture. For the most part, they are now machine independent. They can be used on any type of hardware or software combinations. And again, remember those early languages that I talked about as being Fortran and COBOL. Third generation languages, they work by using something called primitives. The primitives are going to correspond to machine language on that one-on-one basis. Now, just like assembly uses that assembler to do that translation, third generation languages also have to be converted to machine language. So in this case, we've got something called a compiler, or for scripting, more scripting languages, they're called interpreters. So Python actually does use something called an interpreter, and that it just means that we can it executes line by line as opposed to having to write several lines of code and then compiling all at once in order to get it into a state that the computer can understand and then can run. Now, we say programming languages are formal languages, and what you speak is considered a natural language. This just means that natural languages evolve over time and they kind of come about organically. Formal languages all have grammar and such defined as you're developing the language, okay? So we can see here the generations of the formal languages are linear. They're really not linear. That's not really what happened. But let's go with the linear for now. With the lower numbers being closer to being able to speak the binary of the machine, and the higher numbers getting as close to that natural language or what a human would speak as possible. Okay, well, again, didn't happen in a straight line. It happened more like what's in the graphic to the right. You can see it's taken on a few different approaches, and we call them programming paradigms. So let's look at, we're going to look at those paradigms that were called functional, object-oriented, imperative, and declarative. Now, the imperative is a traditional programming process. That's kind of what we've talked about. That's where Python lies. You can see there Python is actually under the 1990. It's one of the more recent ones. Object-oriented is very closely related to imperative. It uses something called an object. An object is going to be self-contained with data and actions called methods, related, encapsulated in a single unit. But object-oriented and imperative, very, very closely related. Now, in contrast, we've got the declarative and the functional. So the declarative has the programmer describe the problem instead of the algorithm. So this is where your SQL, if you know SQL, which interfaces with databases, that's where SQL lies. It uses pre-established algorithms. So you're going to use algorithms that already exist and put them together in a way to make them work for you. On the other hand, you've got the functional, and this is going to be looked at kind of as a black box with input and output. But again, you're using a bunch of predetermined algorithms to complete the tasks that you need. You're not going to be able to manipulate the algorithms as easily as you can in the other two. This example shows what a functional paradigm looks like. You can clearly see the inputs and the outputs on the yellow and the red, with that black box in the middle. Now, this black box happens to be a combination of 3 different algorithms, a find sum of 2 of the inputs and a find sum of the third, and then a find difference, okay? So it's using predetermined algorithms and with the different inputs to create an output. So let's shift more back towards the more traditional programming concepts and what those look like. So high-level languages use many different types of abstractions. Now remember, abstraction just means a simplified version of something technical. We don't want to see the nitty-gritty. We just want to, you know, kind of have an overview of what it does. We don't care step by step how it does it. These abstractions can fall into different categories. We've got simple, such as constants, literals, and variables. We've got complex, like statements, expressions, and control statements. And then we have esoteric. Esoteric means it is going to be specialized or individualized. Those would be your procedures, modules, and libraries. But we do have the ability to use all of those items in our toolbox. But in general, your program is going to have 3 different types of statements, okay? You're going to have a comment statement somewhere in your program, hopefully if you're a good programmer. You've got declarative statements, and then you have imperative statements. Imperative statements are the steps of the algorithm, okay? Those are your work steps, the process that you go through. The declarative, on the other hand, that is going to define terminology and data that you're going to use within those imperative statements. We've already discussed comments, so I'm not going to put that out there. Typically, in good programming practices, your program is going to have some sort of structure where your declaration statements are going to be closer to the top and your imperative statements are going to be towards the bottom. But what types of declarative statements can we do? Well, we've got some different things that we can do. We've got something called a primitive data type. Remember, declarative is just reserving that memory space. We talked about that in lecture 1. So a data type describes the type of data that's going to be stored at that memory location. Here are some basic primitive types that can be found in all languages, okay? And I've also put next to it the syntax that we've used in Python to maybe make some sort of connection. You can see here, as far as data types go, all programming languages have some type of whole number or an integer. They've got some kind of decimal number or a float or a real. There's a few different ones out there. We do have a character, which is a symbol, and we've got a Boolean, which is that true false. And that Boolean, that's that true false we used back in those logic gates in lecture 1. Here in Python, we've used the words int, we've used the word float, char, and here we did an int with an actual assign statement. So those are some of the things that we've done within Python already to use those primitive data types. Now, on the other hand, a data structure is a conceptual shape or an arrangement of data. For example, a string is a list of characters. That's all it is, okay? One of the most common structures is an array. An array is just a block of data with the same primitive data type. You can have a one-dimensional array, which just would be a list of data, or you can have a two-dimensional array, which would be a table with rows and columns, kind of like what we have here for an example. So you're going to refer to the cells by row and column number. So for both of these examples, we've got 2 different languages here. We've got C and we've got Fortran. If you look at the statements over here that I have on the left, both of them somehow state that I'm going to have 2 rows and 9 columns. They're stated in slightly different ways. In C uses an int, Fortran uses the word integer, slightly different. Now, the big difference comes in when you refer to those cells. Fortran starts its numbering system at 1, and so you can say row 1, I'm in row 2, and in column, I'm in column 1, 2, 3, I'm in column 4. Okay, so that's where that 2, 4 comes from. On the other hand, C starts with a 0. So that's actually row 0 and row 1. That's where the 1 comes from. And we're actually in column 0, 1, 2, 3, 3. So there's a slight difference. You need to make sure that you understand whether your counting starts at 0 or 1 based on your programming language. Just know that it's something that's out there just in case you get hung up. Let's take a look at a more abstract example. Now, you can create a data structure with anything. So you can create your own data structure. This is what we're doing in this example. So here's the code at the bottom that is creating a data structure called an employee. This structure is going to combine 3 different pieces of data. You're going to have a name, an age, and a skill rating. So now these 3 pieces of information are always connected, and it can be looked at as different fields within this data structure. So it's a good way to keep things that are related together in one spot. We've talked about assignment statements in Python, but let's just take a quick look at a few different languages and what assignment statements looking like in those languages. All of these are going to do the same tasks when it comes to the machine language level, but the syntax is going to be just a little bit different at this higher level language, okay? So let's look at, we're going to take a look at that first one in C, C++, C Sharp, Java. You know, you're going to have Z equals something. Okay, that's going to be the assignment. In Python, we have the assignment statement of just a single equals as well. Here, the difference is there is a semicolon at the end. You can see in ADA, it actually has a colon equals for the assignment, and in APL, you've got the arrow. So all three of these are going to do exactly the same thing. It's just a different syntax. Now let's take a look at control statements. These are going to be slightly different. Remember, control statements go around that sequential tasking. So the simplest way, which is quite outdated, is to use a goto. Gotos were available in very early programming languages, but they kind of caused a little bit of chaos. Led to something called spaghetti code. If you take a look at this goto, you're going to go to 40, then 40 takes you back to 60, and then 60, I don't know where to go after 60. So there's a much easier way to write this as a single statement as on the right. So this is a single statement using an if else. Again, both of these are going to do the exact same thing. It's just the syntax in which it uses. Let's go ahead and expand it just a little bit further. We're going to take this, we've seen the if else in Python, that's the first one on the left. You've got your if, your colon, your else, your colon, and your statements and your conditions in green. Now, if I were to do an if else statement in C, C++, or Java, it might look something like what is on the bottom left. If condition statement A, semicolon, else condition or statement B. Little bit different. You can see the differences in it, but it's still doing the same thing. Last but not least, we've got ADA over here. We've got the word then, and then we have an end if. So that's a little bit different for that language as well. Now let's look at another control statement that we've looked at in Python before, the while. In Python, we've seen while condition colon, and then the body or the steps that we want it to take if that while is true. The same can be executed in C. Notice the biggest difference with C is that it has these curly brackets around the word body. That's how C and Java indicate that that is the steps that are going to be looped with that while or grouped with that while. In ADA here, you actually have words like another keyword here as loop, and then you've got the word end loop with a semicolon. Again, in the end, the structure, the pseudocode, those are going to be the same. It's just the implementation of it depends on which programming language you are using. Comments, my favorite. So we've talked about comments before. I'm not going to linger on it too far. They're written within the program for the programmer, not the user. Remember, they're helpful if someone else reads your code. If you read your code quite a bit of time down the line, they're completely ignored by the compiler. So here's some different ways to actually write comments. I've included C and Java along with the Python that we already know. The Python, as we know, uses the hashtag or the pound sign, if you want to call it that, for comments. In C and Java, they actually have two different ways to do comments. There's a single line comment, which is a double slash, which is the one in the middle. And there is a multi-line comment, which is a slash star, which you can see on the front. Or on the top, sorry. In the end, every language has some way of doing a comment and making it easier for programmers. Now, let's take a look at procedural units. Now, procedural units, that's what you're going to break that program down to make smaller, more manageable, more workable, things. These can be called subprograms, subroutines, procedures, methods, functions. They all kind of have lots of different names, but they do the same thing. Regardless of the language, it's going to start with a header of some sort. The header is going to do a few different things. It's going to identify the name of the function and the parameters or arguments that are going to be sent to that function. Functions can create their own variables, or they can use the ones that are in the program. That is going to be our local versus global variables. So local variables are ones created within these functions and subfunctions, and then once you're out of those functions or subfunctions, those variables cease to exist. they're not a thing anymore. So they can't be used outside. Now, global, on the other hand, can be used anywhere in your code. Formal versus actual parameters, we're going to get into a few slides of that. And then finally, we're going to wrap up this section with talking about passing parameters by value versus reference. The easiest way to do this is by picture. So I'll just wait until we get to that slide. So first, let's talk about the control of a function. So a function itself is the instructions to perform a task. We say that control is transferred from the program to the function at the time it's needed and then passed back to the program once the function completes. For example, we have a program here on the far left. It's going along doing its steps. It gets to a point where the function is needed. That's that big red dot on the left-hand side in the column. At that point, the control then goes from that program into the function at the top of the function. The function then executes all of the steps within the function, and then when you get to the end of the function and all those steps are complete, it returns control to the very same location in which it left. Okay, now that we understand that, let's take a quick look at what these function headers look like and the information that's contained within them. Here's an example of a function written in a language using C. Again, depending on the language, the syntax might be slightly different, but the idea behind it is the same. Okay. This header with C, it starts with the word void. There usually is some sort of indication if something is being returned for the function. In C, since there's nothing returned, it uses the word void. Next, there is a function name. In this, it says project population. That's the blue text that you can see. And you can notice, again, no spaces. It kind of follows those same rules that variables follow, except that in C, we're going to have a capital P. No big deal. Finally, within that header, we've got something in parentheses called with float and growth rate. This is going to be the arguments or the parameters. The arguments are going to indicate what primitive data type it is. So here it's a float, which means it's some kind of number with a decimal point, and the name that that variable is going to use. So in this case, we're going to use growth rate. Now in C, we've got those curly brackets to contain this function within, and what's in those curly brackets are all the steps within the algorithm. So Python doesn't use those curly brackets. This is unique to C and Java. What's not unique though is the use of the header. And then after the header, you can see we've got the int year. Don't forget that's that declarative statement. Remember, we're declaring the variable. And then after the declarative statements comes the imperative statements. Those are going to be your processes and all of your calculations that you're going to go through step by step. Let's take a look at passing by value versus passing by reference. So first, let's look at pass by value. When calling of the function, okay, remember we said that call, it goes from the program and jumps to the function. When that happens and there's an argument, the argument is then sent to the function to use. Now, when you pass by value, a copy of that initial variable is then made for the function to use. Okay, the function can then manipulate it, it can change it, it could do whatever it wants to that variable, and it has its own copy. Now, once it goes back to the original program, that copy no longer exists, it disappears, it's gone. But no changes were made to the original because we made a copy. Now let's see in contrast what pass by reference looks like. Big difference here, right? Now the difference is that the program and the function are both looking at the same variable. That copy, we don't make that copy anymore. So passing by reference is passing the actual memory location and not a copy of the memory location. So now if the function changes the value of that variable or manipulates that variable in some way, it changes everywhere and for everyone. Okay, so you can see the difference in the graphic. In the formal box, there's no longer a box there with the number 5 and then the number 6 and then it's gone. It's actually using the variable that's in the program that sent it. So remember, it's using the same variable and it's not using a copy. getting on towards the end, this is the last topic for this lecture. We're going to talk about language implementation. So we're going to talk about how we convert that high level language into that machine language that the computer can understand. We call this translation. There are a few different steps. But first, what the programmer writes, we're calling that the source program. That's all the way over here on the left. And what the computer can understand is called the object program. That's right there. So each translation has 3 steps. We've got the lexical analyzer, the parser, and the code generator. The lexical analyzer, this is going to recognize the sets of characters and those keywords, and it's going to break it up into things called tokens. The tokens are then going to be grouped into statements by the parser. But the parser is going to take those statements and create parse trees out of it. The parse trees then go to the code generator, and the code generator creates the object program. We're going to look at the control statement of a simple if just to end this lecture, but there's a lot more that is available in the book when coming to parse trees. Go ahead and read through it. You really don't need to know that much information about it for this course, but it is kind of an interesting thing. Maybe it's only interesting if you have insomnia. I don't know. So the parsing is based on rules, and these rules are set by the programming language grammar. This is what you call a syntax diagram. This is showing what Python's if then else statement looks like. So it's something that you should be kind of familiar with. We can see here that those terms in the ovals, those are going to be your keywords or those key indicators that we use, like that colon. So we're going to start with the keyword if, and then after the if, we're going to have some type of Boolean expression. This expression is going to be followed by a colon, which is then going to be followed by indented statements. This looks all familiar, right? After the indented statements that complete if the true, then we have the else, and then we have the indented statements for the false. That's all there is to it. Notice this is very, very generic. It's just showing the specifics necessary for coding that if-else statement in Python. Again, the book takes this to the whole next level using those parse trees. I just thought it was a little bit too much for what we need for this lecture. So that's all I'm going to put in the lecture for today, because this covers most the main points that I would like to cover that you need to know. So if you have any questions, comments, or concerns, please feel free to reach out to me at any time.